Okay, so let's look at this two component form, these Pauli spinors in, let's see, in a slightly different perspective. We have this sigma dot A, which is equal to sigma 1 A1, sigma 2 A2, sigma 3 A3, which is sigma 3 minus sigma 3, sigma 1 minus I, sigma 2, sigma 1 plus I, no, this is A. A3 minus A3, A1, A2, A1 plus I, A2. Now we already know what our rotation matrices are. So U is equal to e to the power minus I over H bar S dot N, where this N vector we usually define as its magnitude is how much you rotate, is the axis of, and the unit vector corresponding to that vector is the axis of rotation. So if you rotate around this axis by an angle theta, then this n vector is a vector pointing in this direction and has a magnitude theta. Now just for simplicity, let's look at the case where n is equal to theta z hat. So that u will be e to the power minus I over h bar over 2 sigma z theta. E to the power minus I over 2 minus I sigma z times theta over 2, which is e to the power minus I theta over 2, 0, 0, e to the power I theta over 2. Now let's see what this u does to my sigma dot A. This is equal to e to the power minus I theta over 2, 0, 0, e to the I theta over 2, A3 minus A3, A1 minus I A2, A1 plus I A2, times e to the power minus I theta over 2, 0, 0, e to the power I theta over 2. And I will just do the matrix multiplication. Let me first multiply the first two matrices. Well, the first matrix just tells me to multiply the first row by e to the power minus I theta over 2 and the second row by e to the power I theta over 2. Let me do that second multiplication also. Yes, plus minus. So this is plus plus minus minus. Now this will just give me, if you do the multiplication, A3, e to the power I theta, A1 minus I A2, e to the power minus I theta, A1 plus I A2, and minus A3. Which is, by the way, let me just write it as sigma dot A prime. Now sigma dot A prime is just A3 prime minus A3 prime, A1 minus I A2 with primes, A1 plus I A2 with primes. So if you just compare these two matrices, A3 prime should be equal to A3, and A1 prime minus I A2 prime should be equal to e to power I theta A1 minus I A2. The other one just gives the same thing. Now A1 prime is nothing but the real part of A1 prime minus I A2 prime, which is the real part of e to power I theta is cosine theta plus I sine theta A1 minus I A2. Well, if you just do this multiplication, take the real part, that is A1 cosine theta plus A2 sine theta. Well, we can do the same thing for A2 prime. This is the imaginary, minus the imaginary part of A1 prime minus I A2 prime. If you take the imaginary part of that expression, you would get A2 cosine theta minus A1 sine theta. Which is nothing but rotations by theta. So basically this tells us that A, U dagger, sigma dot A, U, this is nothing but sigma dot the rotated A. But there's a problem though. Not really a problem, just an observation. Minus U dagger, sigma dot A, minus U also gives me sigma dot the rotated A. Two minuses, they make a plus. So for every rotation in the three-dimensional space, there exists two different rotations U in the spinor space. So both, if you have one U corresponds to a given rotation, minus U corresponds to exactly the same rotation. So whenever you are dealing with these spin monohalf particles, you always have these additional factors of 2 here and there. It rotates by, the kits rotate by theta over 2, you have two different matrices corresponding to the same rotation, etc. Well, in formal terminology, what we say is, well, these U's are, we will discuss what we mean by SU2 in more detail. These are just 2 by 2 rotations in the complex spinor space. And we have SO3. These are just ordinary rotations in three-dimensional space. For every rotation in three-dimensional space, this argument just tells us that there is 2 elements in the 2 rotations in the spinor states, and hence we say that SU2 is a double cover. So this basically means that for every rotation in three-dimensional space, there are 2 rotations in the spinor space. So do you have any questions? Now there's then the problem of also finding the eigenstates of, let's say, S dot n. Well, basically we already solved it in our first midterm. Let's just find the eigenstates of S dot n. We had already said that 1 plus 2 over h bar. Well, for spin 1/2, S dot n squared is h bar over 2 squared sigma dot n hat squared. But sigma dot n hat squared is nothing but n hat squared, which is 1. Well, that basically tells me that if I construct this operator, well, S dot n is equal to h bar over 2 sigma dot n. So eigenstates of S dot n are the eigenstates of sigma dot n, and vice versa. So sigma dot n, 1 plus, if I multiply this with S dot n, I basically obtain this h power over 2 sigma dot n 1 plus sigma dot n. This is h power over 2 sigma dot n, but sigma dot plus sigma dot n squared, which is just 1. So this is a nice operator in the sense that if I multiply S dot n with this operator, I get the same operator with h bar over 2. Basically, it holds if I multiply it with some ket also. So there is one eigenket of S dot n. Now, sigma dot n hat, well, we already know what this operator is. If you just do the matrix multiplication, this is nx, no, this nz, nx minus I ny, nx plus I ny minus nz. So 1 plus sigma dot n, this is nothing but 1 plus nz, nx minus I ny, nx plus I ny minus nz, 1 minus nz. Well, let's just multiply this with 1, 0. If this is not 0, then we know that this is an eigenket of S dot n. If I multiply this with 1, 0, what I get is 1 plus nz and nx plus I ny. Well, let me write it explicitly. This is, well, n is a unit vector pointing in some direction, which with angles theta and phi. Nz is cosine theta. Nx is sine theta cosine phi plus I sine theta sine phi. This is equal to 1 plus cosine theta sine theta e to power I phi, which I can also write as twice cosine squared theta over 2, twice cosine theta sine theta over 2 sine theta over 2 e to power I phi, which is twice cosine theta over 2 times cosine theta over 2 sine theta over 2 e to power I phi. Well, this is normalized to 1. Well, that is one way of obtaining my eigenkette. Well, there we can obtain the same eigenkette by slightly different means. Let's see. Let's say that this is my n hat direction. I'm looking for a spin pointing in that direction. This is my angle theta. This is my angle phi. Well, I can start with this vector, z hat. I can rotate around y by theta. Let's say this is n hat prime. Then I can rotate this around z by phi. And I would end up having my n hat vector. So basically, n hat vector is nothing but first a rotation around the y by theta, and then a rotation by phi around the z of the z hat vector. Now, our y of theta is e to the power, well, let's see. My claim is that n hat plus state will be of plus k. This is my claim. Let's see if it will be actually satisfied. You see, this was equal to exponential of minus I over h bar sy by theta. This is equal to exponential of minus I over 2 I sigma y theta over 2. This is equal to cosine theta over 2 minus I sigma y sine theta over 2. This is cosine theta over 2 minus I 0 minus I 0 sine theta over 2. This is equal to cosine theta over 2 minus sine theta over 2 sine theta over 2 cosine theta over 2. Now let's look at the other one. Well, if you go back, we need the rotations around the z by phi. This is equal to exponential of I sigma z phi over 2. This is cosine phi over 2 plus I sigma z is 1 minus 1 0 0 sine of phi over 2. This is equal to e to power I phi over 2 e to power minus I phi over 2 0 0. So this ket, the corresponding matrix to this ket, should be e to power I phi over 2 e to power minus I phi over 2 0 0. Then we have, before we have that rotation by theta around the y-axis, cosine theta over 2 minus sine theta over 2, sine theta over 2, cosine theta over 2, and this we are acting on 1, 0. If I make the last multiplication first, this is just cosine theta over 2, sine theta over 2, which is e to power I phi over 2, cosine theta over 2, e to power minus I phi over 2, sine theta over 2. Now if you compare it with the previous expression that we obtained, this was what we had obtained before, and this is what we have now. Oops, sorry, there. I probably have made a mistake over there. No. This is e to power I phi over 2 times that one. Okay, let's go back. Yeah, this should probably be a minus sign over there. But you see, there I probably missed a minus sign somewhere above, but you see, basically I get the same thing. So I can obtain this ket also by rotating the 1, 0 ket. Up to an overall phase, which doesn't change neither the normalization nor the eigenvalue. Oh, sorry, here I have a minus sign. The rotation matrices has the e to the power minus I over h bar s set. So here is the minus sign. So here a minus. So here is a minus sign. So this is minus, this is plus, this is minus, this is plus, this is minus, this is plus, this is minus, this is plus. So I have a minus over here, a plus over here. So this is minus. So basically, we have two methods of constructing this eigenstates of S dot n. If you want to look for the plus eigenstate, you start with the plus z direction and just rotate that to the n direction. Or, this was the question that I had asked you in the first midterm, just use the projection operators. So whatever ket you start with, if you act on that ket with 1 plus sigma dot n, you obtain an eigenstate of S dot n with an eigenvalue h bar over 2. If you want minus h bar over 2, just change the plus sign over there to a minus sign. Okay, any questions? Okay, so see you on Monday.